Alright, well welcome to Chapter 3 of the Database Management course using the Cornell textbook. Going to be going over in detail now that relational database model. We've looked at the different models available that have been invented. There are newer models out there, but the relational model is the one you need to start with. That's what MySQL uses, that's what Microsoft SQL uses, Postgres, Access, many other databases you will use that, and you'll build your database knowledge upon that. If you get into databases, you could actually have a career just being the database manager, the database expert, because they are not easy. It's like a different world from the programmers. If you program, especially if you do scripting on servers, or you deal with databases, knowing how they're formed, mostly relational models, will allow you to pull data out of databases. You compose queries, you execute queries that do create, read, updates, or, you know the word, delete. Okay, so in this chapter, going into the details of the relational model, I'm going to learn about the remember, it's a logical view of the data. Logical view, not a physical view. Meaning, we don't care how the data is stored. I can go hunt down in var-lib MySQL and dig through the files and look at the physical view, but to the database programmer or the person getting data, all you think about is the logical model, logical view. Instances of entities being read out of the table in a select query. And in that query, logically, it may look like you're getting data from multiple tables. We leave it to the database engine to pull it out of its whatever format it has that information in. If I go dig through the files that the database engine is using, I may find that every table is a separate file, but that doesn't matter to me. Relations are the component. There's relationships are not the same thing as relations. Relations is the idea that you've got rows, tuples, and columns, attributes. Sometimes they're called fields. Think of those columns are the attributes of an instance of an entity, a tuple. And the relational idea is implemented as tables. So you're learning the logical format of things. And now we're going to start looking at the operator on relational databases. How we get data out, how we compare data from two tables. Oh, so much fun stuff. And the bad thing about data redundancy. We don't want data redundancy. Indexing is key to finding the data quickly. That's why we have primary keys. Okay, so a logical view of the data means I can design how I deal with the data. I don't have to worry about the underlining format. So we have this idea of this relation construct, and we'll see it in an example here. Now think about the tables. We've looked at tables, and now you got to get a good handle on the terminology. The terminology for tables is that table is a logical two-dimensional structure with rows and columns. In a row of the table, that is an entity of a single occurrence of that entity. I call it an instance. They're calling it a tuple. Others will call it a row or a record. Access calls them records. Records, rows, tuple, an instance of an entity. And the entity is the name of the table. The columns in the table are attributes with distinct names. We call them fields. Some people like to make them all caps. I think that's very ugly. I like to mix. I like camel case, easier to read. Spaces are usually not there. Some may allow spaces in the names, but most databases you'll see all caps with underscores instead of spaces. When I'm reading a single piece of data and information about one instance of the entity in the table, we call that a single data value. Remember, as we're setting up the table, everything in one column must be the same type, same format. Now, some of the formats are very flexible, like text. Well, that could be anything, but everything in that column can be text. A little more stricter definition, when I have an int as a column, everything in there must be an int. So I'm controlling how the data gets into my table, because that will be very important. As I'm reading data out of tuples, I need to know that the fourth column is the birthday or is the cost. Every time I read a tuple from a specific table, I know which column has what kind of data. And that domain, or the range of values that are allowed, that you program in when you design your table, and the restrictions or the requirements, that's what they call the attribute domain. Another term, I just call it the requirements, or the required values, or validation rules that Access uses. And how the data is stored, it doesn't matter, because the primary key finds the rows that I need, the rows or columns. Well, the primary key finds the row, the column, the row, the names of the columns. That's how I get at the data, not by the fourth column. I don't care what number column it is. I care about the title of the column and the key of the instance of the entity or the tuple. Every row, if we are to use it in the relational database and to work with our scheme, must have some combination of attributes that uniquely identifies the row. And all the databases I've seen, the cleanest way to do that is you have a primary key. The record has an ID. But that's not necessarily required. You can actually combine something like phone number and zip code to identify a unique entity. Or first, last, middle name, and phone number. Some databases, keeping track of your interaction with a website, will have a unique combination of your IP address and your MAC address to identify you. And I'm pretty sure TeamViewer does something like that. When it discovers I have tried to use it on too many machines, suddenly my PC at my address is no longer accepted to connect. It says, sorry, you've been detected to be running in commercial environment. So I've been using remote PC instead. Okay, so those are some of the terminology that you need to be pretty solid on, because they're going to be coming up the rest. So study those terms and make sure you understand what we're talking about, and we'll try to use them consistently. Now the keys is that unique identifier of a row. We keep coming back to that, uniquely identifiable, because remember, we are storing data, millions of records of data in some cases, trillions of records of data in some cases, terabytes of data as we gather weather information, for instance, or astronomical information. We need to identify which item in that database is the one I want to extract or read. Well, the key allows me to identify that. From then on, whenever I need that specific row, I don't keep track of all the data. I just need the key to that row. and the database goes and finds it in the most efficient way that it knows how, based on some cool things it does with sorting through. When I ask for a particular key, it can find it super fast. That's why we index. We make actually a separate table so I can search for the right record given a key to that record. We'll be discussing that some more. Now, determination means I know a specific row or instance of a row in a table, and I can determine that row based on some known attribute. The primary key is the best thing, or like I said, a combination of attributes that determine exactly one row. A query is often indeterminate. I say, give me all the records whose phone number starts with 563. That does not determine the value. It determines a set from my table of members in a table, but it does not determine one other thing. And another, a key determines the rest of the information that goes with that exact record or tuple of data. And as we design our database, it's all based on what data is going in there. And a term we're going to use, functional dependence, mean I have one value, they determine some other values. So first and last name and social security number, that should determine the address, the student ID. It should be unique, and it determines other attributes of my record. The determinant is what determines things. Again, this is usually the primary key. Attributes that then go with that specific record are called dependent attributes. And when we talk about some theory here about what items are dependent fully on one key, we call that full functional dependence. And then you have a valid relationship. So it's all the terminology and the logic and the thinking behind this logical model of a relational model that we call it. Now, as we're going to be spending some time on keys, we have keys that I like most. I don't like composite keys. I like just one primary key. And that's the name of that attribute is like the ID. I usually use the word ID. Entity name ID, like employee ID, invoice ID, and that's very common. But sometimes it may be multiple columns make the unique attributes, and we call that the composite key. And if there are multiple attributes that make our composite key, they are called key attributes. Each entity has its own unique identity. Then we know we have entity integrity. Relational databases don't work unless we have entity integrity. So we're going to make sure as we design our tables and the logical construction of our tables that primary key is unique and it cannot be left blank. It is a required field. It is not null, and there is a little check mark, not null, when we create the table. Keys can never be blank because that means that there would be other blank ones that would make them not unique. So just the rule is it can't be left null. Even though if only one of them nulls, you might say, well, it's unique. No, we don't allow null. It can't be blank. But you can choose what type of data it is. It could be text, it could be numbers, it could be a large integer. I usually use a large integer thinking I might get a huge table, and that primary key I leave as an integer. And partly because the databases I've worked with have always had that one primary key, but it's not absolutely required. If I have a null key or a null key attribute, I could have a problem. I'm missing something. I have an error. It's inapplicable. It should never happen, and the database should not allow that. Now here's something we do cover in Access. It's probably as deep as we get in the fundamentals course, thinking about databases. I always kind of state it this way. If I have in my camper database, a table of counselors and table of campers, and my camper comes in and he has a reference to a counselor number 23 or cabin 52, but we have no actual counselor 23 or no cabin 52 in the counselors table or campers table or cabins table, I have just lost my camper. They don't have a counselor, they don't have a valid cabin, and therefore we have violated referential integrity. We're not referring to an entity that exists. That would be breaking referential integrity. Sometimes they call those orphaned records, records that don't have a needed reference. Sometimes there's a secondary key just for retrieving things from a query, such as a phone number is a great way to do that. That key may be unique to most records, can perhaps even work as a primary key if it is unique to all of them, but it's not officially the primary key. We call it a secondary key. Okay, now using those terms now, here we have a product table and a vendor table. And we see now they're using code. I would prefer ID. The best thing to do, use the same word from table to table. That's actually not required. You don't have to have this say vend code. This could be called vend ID or VID, and this could be called vend code. As long as somewhere in the metadata of your database you tell the relationship, or you establish the relationship that vend code relates to the vend code in the vendor table. Now let's see if we have referential integrity. Is every one of these codes referring to an existing vendor? Yes, 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 and yes. We see we're referring to two of the same. That's not redundancy, because that's a primary key of this table. It's okay if we started keeping track of contact here and area code and phone number here in this table as well as here. That would be a bad thing. That would be redundancy. Now the product code for our products appear to be unique. If we've made it the primary key, yes, we have made it the primary key, then the database engine would not allow us to enter a tuple or a record that had a duplicate. It would actually give an error. It would refuse to update or create a record with a duplicate product code. That's the rule for primary keys. So simple relationship between these two tables. The relation of the vendor code here is referring to the primary key in the table here, vendor code. Now this is the one side. Vendor code is unique. This is the many side. The vendor code could appear in multiple records in this table because it's the one to many relationship. In SQL and in MySQL, there is never a many-to-many relationship. There's always a relationship to the primary key on one side, and that primary key is included in the many on the other table. You logically may think of a many-to-many relationship, but in the actual table design, you have to have a table in between that can have many to one back to many. And we'll show that as we go through some designs. Now, as we think about keys in our tables, there's these terminology that we use. Now, I don't like Again, I'd like just one key, but they have a super key that identifies each row. To me, that's the best thing. We may have a candidate key. It doesn't contain other attributes. It doesn't have a subset of attributes. It's irreducible. A primary key, it identifies all the other attributes. I love that. When I'm referring to another table by its key, we call that the foreign key. And here we see that vend code is a foreign key, meaning it's related to the primary key in another table. That's the foreign key. And a secondary key, just for other data retrieval purposes, such as phone number or area code, I can possibly use a secondary key, but usually you have one primary key. Now, as we talk about integrity rules, here's a few that go with primary keys. They're unique. They cannot be null. We already looked at that. Its purpose is it's a unique identity. A foreign key references other primary keys in another table. That's another rule about integrity. An example of integrity is you can't have duplicate invoice numbers. You can't have blank invoice numbers, meaning all invoices are uniquely identified by their invoice number. There's nothing else needed to find the correct invoice except what's the invoice number. You get everything from there. Referential integrity. Foreign keys. You're referring to a key. Remember, that's the camper's, who his counselor, or what his cabin ID is. Well, if it's null, he has no place to go. And it matches something in an existing table. It's not null in another table. It must exist, must reference an existing primary key. Referential integrity. And the reason for that is you don't want to have orphans. You want to have data that is related. You don't want to have orphans lost and not redundant data, worthless data filling up your database. And their example is a customer does not have an assigned sales representative. And according to the business rule, a customer must have a sales representative. And so that goes back to the business rules you need to understand when you're working with databases. Now we're looking at integrity rules here. Do we have a broken rule? Well, I see one right here. We don't have an agent referred to by customer 10013. Now there may be other fields about agents that we're not listing here. We can, when we're retrieving data about agents based on their primary key, often in a query we don't do a select star, which gives me all the columns. I can select just the ones that are of interest to me for that particular need of the data. So there's a broken rule. This customer has no agent. Now, of course, if you modify the business rule that, oh, okay, customers don't always need to have an agent, we'll assign one later. Well, then you have to specify that in your documentation. But you have a broken relation. You have an orphan customer. You may have actually a script that you can go through all your customers, find those, do a query of customers that have a null agent code, and assign a default agent to all of them. As we design our tables, we can put those constraints on those fields, and you've seen those check marks in the designing the fields. You can say, yeah, there's typically a check mark in the user interface, is null allowed. Those are important constraints to establish right at the creation of your table. Now there's various ways of manipulating the data in the table, extracting data, comparing it, and we're going to learn about the relational algebra. The rel var holds a variable related to something in the operation. So we're talking about operations or manipulating of data, getting data out to get information out of the raw data, or changing the data, or seeking specific information, even deleting data. So once a relation operator has some closure, we may produce new relations, get new data out. And that's a little fuzzy. We'll look more into that. I can select information from a table. I can project, that's another operator, get a subset of a table, a vertical subset, a particular column. I can extract a union of data between two tables. And I can make sure it doesn't give me duplicates. If two tables contain the same row, the union excludes a duplicate. But a union combines all rows from two tables. Now, two tables are not union compatible if they don't have the same number of columns, and every column has the same data type or compatible domain. An intersect operator between two tables gives me only the tables that appear in both of them. Again, it doesn't make sense if the two tables don't have the exact same number of columns with the same data types. Here's a select command. Select all gives me basically a copy of the table. Now this is a temporary, think of this as temporary list of what it found in the table. A select all or select star retrieves a table in memory or a temporary table, an exact duplicate of that table. If I select only the price less than $2, I am essentially running a query where price is less than $2. And depending on your database language, the actual language will look a little different based on whether you're doing MySQL or Microsoft SQL. Most of the time, they look exactly the same. If I only want a specific record, I'm saying give me the star where P code equals a specific number, product code. And knowing the product code is a primary key, then I know I will get one record. But of course that assumes I know the structure of that database table and that primary key is there. I have gone partway through this chapter. We'll look at a few more and then I'm going to stop and let you work on the next Microsoft SQL simulated certification exam where you will import data. Let's finish up here. We got a couple more slides that talk about these various operations. Now the project operation is a operation that not all relational databases may have. I've never used project inside of MySQL or SQL. I just select a column of data, but they call it a project. Select price or project price means give me just the price data from that table. I would use it as a select price from the product table. Project two columns gives me just those two columns. So in SQL, project is equal. I can use select to get the equivalent of a project, give me the results, or getting the contents of those two columns. How we sort this depends on if I add additional modifiers to this project, like order by, or order ascending or descending, or sort, depending on the language you're using. Similar to this one, code and price gives me those two columns. So project gets me a specific column. The union, as we think about two tables with the same exact number of columns, the same data types, combines the data, not duplicating information. So I'm not going to duplicate the box fan. It's in both tables. I only get one box fan over here. Otherwise, I get the combination, combined. Think of it combining those two tables. The intersect, the thing that's only unique between the two tables. So when I have a list of your boggle words, the intersect shows me the words that we both had the same. The intersect. There's also difference and product. Now the difference, similar to the union, I have to have tables with the same number of columns. This one is pretty crazy. This gives me all possible pairs. So you get a huge result out of the product. Here's the difference between these two tables. The thing that's not in both, or the data that is in, is one and not the other. So George, not in here. Jane, not in here. Peter, not in here. Franklin is in here, so he's not included. Martin is in here. Susan doesn't appear because I'm subtracting these from this. I don't leave Susan around. So the difference is not the same if I do it the other way around. Not commutative. And here's the crazy thing. For every record in here, it's list every record here. So for every flashlight, I list each store. So 3 flashlight, store, store, store. Lamp, store, store, store. The product of the two. Now, when this is useful depends on my application. Okay, we're going to stop here. Give you time now, the rest of the class, bring up that next assignment for managing Microsoft SQL. You're going to learn how powerful the import can be. So bring that up in Schoology and walk through those. Take screenshots of each as you go, as though you're taking a certification test and you're producing the answer. I will stop here, and on Wednesday we'll go through these operators and maybe even do some of these, begin some queries using these kind of operators with our database. I'll stop right here.